we are told that a Carnot refrigeration cycle operating in saturation dome. So a Carnot refrigeration cycle is executed in a closed system in a saturated liquid vapor mixture region. Using this, we are given a mass of refrigerant, and that refrigerant is actually refrigerant 134A. So this is actually the total mass. That's the total mass. That's the total mass. And that total mass is equal to what? Is equal to 0.8 kilogram. Make no mistake, it's important to know that. And the mixture, the maximum and minimum temperature in the circle are 20 degrees Celsius and minus 8 degrees Celsius. It is known that the refrigerant is saturated. It's saturated liquid at the end of the heat rejection process, and the network input to the cycle is 15 kilojoules. So what is 15 kilojoules? What is 15 kilojoules? So 15 kilojoules is actually, let me underline that, it's actually the value for the work into the system. 15 kilojoules. And we look carefully, we need to determine the fraction of the mass of the refrigerant. So make no mistake, from quality, we can say that, so step 1, we read the problem carefully, and step 2, we get the main formula to solve the problem. Now, but from the question, we can say from quality. Quality is given as X, as I always say in class, and that quality is defined for the mass fraction. So the mass fraction is equal to what? Which is this mass fraction, remember, is quality. Is equal to what? The mass for vapor over the mass total, which somebody can say mass vapor over total mass. That is actually quality, which is same as the mass fraction. We know this is equal to what? 0.8 kilogram. And our main problem now is to determine the mass of vapor. So this mass of vapor now is our main problem. How do we solve for the mass of vapor? We solve for the mass of vapor by looking at the expression for the coefficient of performance for the refrigeration, for the refrigerant. And what is that? We start by looking at the coefficient of performance for the refrigerant. And for a Carnot cycle, it has to be 1 over temperature for the high pressure line over the temperature for the low pressure line minus 1. Remember, I said for the Carnot cycle, you must convert the temperature to Kelvin. So the temperature for the high pressure line is 20 plus 273. That is in Kelvin divided by minus 8 plus 273 Kelvin minus 1. and if we divide that and we subtract 1, we are going to have 9.464. And like I said, the coefficient of performance for the refrigerant is not having any unit. And because we have the coefficient of performance for the refrigerant, we know that the heat for the low pressure line, which is actually given by the system now, where heat is lost by the system. So no, heat always lost on the system in the high pressure line, and heat comes to the system on the high pressure lines. But heat is lost on the system in the low pressure line, which can be towards the earth or it can be in a reservoir, but heat is gained to the system through the high pressure line or the high temperature line, which can be a furnace or an engine or a combustion cycle. So the heat loss for the system now, in this case, will be the coefficient of performance for the refrigerant times the work into the system. And this is what we just calculated here, and the work into the system is 15 kilojoules. It's actually 15 kilojoules. So we have 9.464 times 15 kilojoules. So I have 142 kilojoules, and therefore we can be able to determine the heat loss for the refrigerant for what? For a given property. And for that property, now we may want to go to our system of enthalpy, which talks about the enthalpy of vaporization for the refrigerant, which is 134A at minus 8 degrees Celsius. And if we look at the property for that vapor, we are going to have 204.59 kilojoules per kilogram, and we are using table A11. So we are using table A11. Table A11, and that table A11, we use that property to determine the heat for the low pressure line for that refrigerant for a given mass of vapor, which we have for given enthalpy at minus 8 degrees Celsius, and therefore we can talk about the mass of vapor, which is going to be 142 kilojoules over the enthalpy, which is 204.59 kilojoules per kilogram, and this value becomes 0.694 kilogram, and therefore we can talk about the mass of fraction. So the mass of fraction. Now we know the mass of vapor over the total mass, and this is going to be what? It's going to be 0.694 kilojoules over the total mass, which is 0.8 kilogram, and this is going to give us 0.868 or 86%. And for the pressure at saturation, we just go to the property table. We say the pressure at saturation for the temperature of 20 degrees Celsius for that particular fluid, which is refrigerant. On property table A11, we are going to have 572.1 kilopascal, and that is actually the solution for this problem. So we have the mass of fraction and the final temperature for the system given as such. So look at this problem carefully, and let's look at the last problem. Thank you.